So here we're solving LeetCode code number 713, subarray product less than k. So the idea here is we want to essentially find the number of subarrays whose product is actually strictly less than k. In other words, we can't have a product that is less than or equal to k. It has to be strictly less than k in that it cannot be equal. So that's the idea here. I'm going to essentially uh, sort of talk about some edge cases before we get into the more relevant part of this solution. But the idea here is that we are faced with three constraints. And the first constraint is that k is allowed to be zero. It can even be less than zero, and it can even be equal to zero, all the way to 10 to the power 6. But it's interesting. So as we move on here, we see that each of our elements, nums of I, can either be between 1 and 1,000, or equal to the endpoints as well. And the length of the array is guaranteed to at least be 1. So we're guaranteed an array that at least has one element. And so I want to sort of address a couple things here. The first is that if k is actually 0, what are the implications of this? So if k is 0, and we are supposed to find numbers that are strictly less than k, that means we want to find a product that is less than 0, strictly less than 0. Well, it's kind of counterproductive to do that because the numbers that we're given are always positive. So how can we find a product less than 0 if the numbers are always going to be greater than 0? In fact, they'll even be greater than 1. That means if k is equal to 0, then there actually won't be any solutions. We're going to return 0. The count of subarrays whose product is strictly less than k is going to be 0, since these two pieces of information lead us to that. Well, what about if k is equal to 1? What would we sort of do in this case? If k is equal to 1, that means we want to find a subarray whose product is strictly less than 1. Well, that just puts us in the previous case, doesn't it? We're finding subarrays whose product is less than 1. That means 0 and negative numbers. Well, 0 and negative numbers are not even allowed on our interval. It can only be from 1 to 1,000. That means in this case, we also return 0. Okay. But we can't keep doing this, right? It's clear to say that if it's 0 and if it's 1, then there will be 0 solution. So we'll return 0. But it can also be negative, right? It could be negative 10. What do we do in this case? Well, what we can say is if k is less than or equal to 1, then we will return 0. So this grabs all of the negative numbers that k could be, and it also addresses the fact that if k is 1 or if k is 0, we want to return 0. I have summarized this in this paragraph here if you would like to look at the reasoning. K being 0 would mean that we find a subarray whose sum is less than 0, but the constraint is that all the numbers cannot be less than 0. They have to be 1 or greater, meaning that all our numbers are positive. So regardless, if they say k is 0, you can't find a subarray that's less than 0, whose product is less than 0. 0 subarrays would be the answer here. And then, of course, the same thing with 1. It's not possible if the constraint is this. Our values are only allowed to vary from 1 to 1,000, and there will at least be one element, right? So what would that bare minimum array look like? It would be an array of just 1, right? And that has 0 solutions, right? Because we can't find a subarray whose length is less than, or whose product is less than one, if we're given an array of one, right? Or and so all of these things kind of hold here. Um, so so we've addressed this first part. If k is less than or equal to one, return 0. The rest is sort of just a standard sliding window problem. It's a variable sliding window. So we'll have our left and right pointers, and while that the right pointer doesn't get close, while r is less than nums.length just means that r can essentially iterate through the array, touching all of the valid indices. We know that nums.length holds the total number of elements in a given array, and if r is allowed to vary throughout the indices, then it can at maximum touch the last index in the array, right? And then of course we move r up by 1. Now, as we move through the array, we're essentially going to build a product. So prod will equal to prod times nums of what's contained at the right. So this is our way of moving through the array and actually accumulating onto itself the product. Prod equals prod times nums of what's contained at the right. And we move right up. But in between both of these pieces of information, or in between both of these lines, we want to, before moving right up, we want to see, well, okay, well, is the product less than k? Is the product less than k? Well, if it's less than k, we want to count and so forth. But I encourage you to sort of look at this in a different manner. As soon as we start off, right? The likelihood is that the product is less than k, right? It's not the case that we want like, give me the product equal to k. If that's the case, maybe it would make sense to build up the product and then, is the product equal to k? But over here, it doesn't make sense to build up the product. Here, we're just finding subarrays whose product is less than k. So the likelihood is that as the first thing that we find, the likelihood is that the product is less than k. Sort of a 50-50% chance there. And so the idea here is that we, instead of saying, if the product is less than k, we'll start by assuming that it is, and we'll say count is equal to count plus right minus left plus 1. So this statement here is it as you add another element, it will count all of the subarrays within it. So if we look at, let's say, this one, a subarray of, let's say, 2, how many subarrays are here? That's 3, right? We have one subarray here and another subarray here, and then the whole thing is a subarray. So you actually have 3 subarrays within an array of 2. And so what this actually takes that into account, right? If you're looking at an array of 1, count is equal to count plus r minus l, which is just 0, right? Because at first the indices pointing to the first element, it's just r minus l is 0, because you're doing 0 minus 0, and then you add 1 to it. So when you add 1 to it, you actually get an array, a subarray of 1, and then we add another element. So remember, count is already equal to 1 from the previous time of doing that. And then we add another element. So count is equal to count plus. So count is equal to 1 plus r minus l plus 1. Right is now 1. Left is now 0. So r minus l, 1 minus 0 is still 1. Plus the 1 that we have here, that's 3. Or that's 2 rather. And then the one that we had before, that's 3. So as we already verified that in an array of 2, there are 3 subarrays. So this kind of does that for us. So we're assuming that as we enter the while loop, we assume as though product is equal to prod times nums of r. We're building the product and we're assuming that, it's a valid case. And then in here, in the middle part, if we have a non-valid case, we basically get rid of that non-valid case and continue counting. So this is sort of like you can imagine a troll on a bridge. It's, it stops you as you're on your way, and it says, okay, well, it's kind of that analogy that I'm doing here. Where in normal cases we're counting up the subarrays, but if the product is suddenly not less than k, so in Java you can't say not less than k, right? I mean, we can't do that. But what we can do is we can say, well, it's not going to be less than k if it's greater than or equal to, right? Because that's sort of the opposite case. If the product is greater than or equal to k, we know it's not less than k. And if that's the case, we are going to eliminate the right part of the window. So what do I mean? What I mean is, so assume we're building the product up, okay, 10 and then 5, which is 50, and we're counting the subarrays as we go, by the way. And then we have, and then 50 times 2, that's 100. The product is no longer strictly less than k, right? And so what we want to do, and so this is where we would be. The product is now greater than or equal to k, okay? So what do? Well, we shrink the window. So we start the shrinking process from the far left. So we say, okay, well, I'm going to remove 10 from the product, right? I'm going to remove 10, a factor of 10 from the product. And then I'm going to move the L pointer up. So what you do is you say prod equals prod divided by nums of what is contained at the left. And then of course you move L up, right? So you can sort of encapsulate that in one line, really. So product is greater than or equal to k, and then prod is equal to prod divided by nums of what's contained at the left. And then so you eliminate the you eliminate that window, and now suddenly you're counting this subarray as well. R minus L plus 1 and all the subarrays in between it, and then you kind of do the same thing moving forward. So as soon as you encounter an unfriendly case, in other words, a case that violates the initial condition, well, then you shrink the window and you kind of move on. You keep aggregating. Now, so another interesting point here is this is not a fixed sliding window problem, right? I mean, I could have, let's say, let's take this example here. And let's say, okay, well, k is equal to 100, wasn't it? So k is equal to 100, 10 times 5 is 50, times 2 is 100. And so as soon as we shrunk the window, it became valid, right? It became valid. But suppose it didn't become valid. Like suppose, suppose there was a smaller subarray that as soon as you you had to shrink again, right? That's what I'm trying to say. Suppose you had to shrink again. Let's say, so you do this 10 times 20 to 100, right? And so we need to sort, we count this one, but then we need to shrink. Well, I don't think this is actually a valid case, but all I'm really trying to say here is suppose we shrunk once and it worked for us, but suppose we had to shrink again, right? Suppose that when this shrinking happened, it was still greater than or equal to the k value. Well, then we would have to do one more shrink. So instead of saying if here, we would instead want to say while the product is greater than or equal to k, shrink, instead of just saying if the product is equal to k, shrink. And then of course we do the counting process, and write plus plus lets us move onward as we do this, and then we just return the count, right? So that's the idea here. And of course, count actually needs to be it needs to be a valid variable in order to be referenced.